Hi and welcome to Physics Kai, and my name is Paul, and today I'm going to go through the multiple choice questions for the Physics HSC paper of 2021. Now, in all my videos, my encouragement to you is to stop the video and actually attempt the questions before you go on. But I also encourage you to download the paper, and the link will be in the description below. Now, before I start, I really value your support, so if this video is useful to you, please consider buying me a coffee. The link is in the description below. So let's get started. So the first question deals with a projectile motion problem, which is from Module 5 Advanced Mechanics. And in this case, what we have is a ball rolling off a floor, and we're asked, first of all, if the ball rolls off at a slower speed, what will that do to the situation? Now, although this is a fairly straightforward question, I want to use this as an opportunity to review projectile motion. We have a ball moving off with a particular velocity, and of course we're going to reduce that velocity as the question demands. And of course it's also going to go down, it's going to accelerate in the downward direction. Now, the time it takes to go down will be independent of what it does horizontally, but the range, of course, is dependent on that time, but also the horizontal velocity. So if it rolls off at a slower speed, the time it takes to go down will be exactly the same, but it won't travel as far. So as a result, when we look at the time of flight, you can see it talks about an increasing time of flight or a decreasing time of flight. It's the same time, so we know those are incorrect. The only thing that can result, of course, is a decrease in range, so B is our answer. Question part 2, which is dealing with electromagnetism, which is module 6. In this case, we have a charge moving in an electric field at a constant velocity, and it says in what direction of the force acting on the particle due to the electric field. It's important to highlight this is an electric field, not a magnetic field. So in the termination of an electric field is that the lines of force represent the direction that a positively charged particle will experience within that force. And since the arrows are pointing up, therefore the force is going to be up the page. Question number 3. Which of the following is not a fundamental particle in the standard model of matter? Now, this is a simply recall question, and in essence it's saying, okay, what is the standard model? What is basically particles are made up of quarks and leptons, and then there are force particles, which are referred to as bosons. Protons and neutrons are examples of hadrons, that is, they are made up of 3 quarks. Going through these options, an electron is a lepton. This is a fundamental particle, so A is not our answer. A gluon is a boson, which is a carrier of, in this case, of the strong nuclear force, and so therefore this is a fundamental particle. A muon is another form of a lepton, basically like an electron except heavier. It's a fundamental particle, and as I've just said, a proton is made up of 3 quarks, so as a result, these are our answer. Question number 4. An astronaut is traveling towards the Earth at a spaceship at point 8C. At regular intervals, a radio pulse is sent from the spaceship to the observer. Now, what's going on here? It's receiving a radio pulse, that is a form of electromagnetic radiation, such as like light. It will always be traveling at C. In other words, you will always observe those types of things at the same speed. What changes, of course, is, for example, the measurement of length contraction, the measurement of time in their respective frames of reference, that is time dilation. So what quantity would the astronaut and the observer measure to be the same? Well, they are in different frames of reference, so as I said, the length will be different, the time will be different, and so automatically A is excluded and D is excluded. But the momentum is something that might change, so it is excluded. So finally, it talks about the speed of the radio pulses, and of course that is C, and so therefore B is our answer. Question number 5. Now, this relates to the idea of spectroscopy, which is in both module 7 and module 8, and so therefore it's got related to absorption lines, as you can see in the question, and also the aspect of stellar spectroscopy. Now, interestingly enough, what we have here is a black body curve, but you see these lines that are dropped. So in other words, there is a certain significant drop of intensity. So what is happening? Well, certain wavelengths of light are being absorbed and redirected away from the observer. So this is clearly about absorption lines. So the question then says, which of the following table correctly identifies the most likely source of the spectrum? Well, that basically means it's more likely to be a star with absorption lines. Now, why are the other options incorrect? a discharged tube will only emit very specific wavelengths or frequencies, and thus it's only related to an emission spectrum, not an absorption spectrum. In both C and D, we have also emission lines, but I've already established it's not emission lines at all. So A is the only possible response. Question number 5. This is module 8, and in this case what we have is an example of a portion of the proton-proton chain. The diagram shows a nuclear fusion process that occurs in stars. What is the isotope labeled as R? Now, in this case, it's actually a skill of reading what is here. So even if you don't understand the process, we just need to see, okay, what is R? We've got, in this case, 2 protons and only 1 neutron. Now, automatically, if it's got 2 protons, it becomes helium, but it has only 1 neutron, so it therefore becomes helium-3, and therefore D is our answer. Question number 7. In an ideal transformer, the current of a secondary coil is 4 times larger than the current in a primary coil. What is going on? Well, let's quickly review the aspects of a transformer. So we have our transformer, which could be drawn like this. And in essence, what you'll have is your primary voltage, which is here, and our secondary voltage, which is over here. And you also have a current, which is IP and IS. The important thing is I've written this as this form because what I end up having here is the power in the primary and the power in the secondary, and if it's an ideal transformer, those two are equal. So therefore, since we're told that the current is 4 times greater in the secondary coil, that means the voltage is 4 times smaller in the secondary coil, and so therefore we have a drop in voltage between the primary and the secondary. Since we have a drop in voltage, that therefore becomes a step down transformer. So the ratio of turns, which is related to this, is also that ratio in terms of primary to secondary. So that follows the voltage. So more turns are in the primary, less turns in the secondary. So we have a drop in primary to secondary, and so therefore we know it's a step down, but because it's a primary to secondary, we have a drop in ratio, it becomes C. Question number 8. Light is shown from a point source of incident upon a circular metal disc, forming a shadow on the screen, but a bright spot is observed in the center. What is going on? Well, light is hitting these edges of my metal disc, but they diffract, that is, they bend around those edges along all of the path of the disc. And so we have light here basically arriving from those edges, but they're all arriving in phase, so they also add up. Therefore, there is constructive interference. And so this is an example of both diffraction and interference, and it's therefore none of the other options. Question number 9. A mass M is positioned at equal distance from 2 identical stars as shown. The mass is then moved from a position X, from M there to X. And what is the graph that represents the gravitational potential energy during this movement? Now, the thing to remember is the definition of gravitational potential energy. That is, what is the energy when we do the work on it, moving from a point of infinity, so really, really far away. And so that formula is U is equal to negative G, capital M, lowercase m over R. Now, in the case of where it is at M, it will have a certain amount of gravitational potential energy. And so therefore, it's got to have some sort of value that we have listed over here. Now, at X, it's the same of value, so it definitely has to be the same on the other side. What happens as we move into it? Well, the value is going to get more and more negative. Why? Because the actual effect will be a drop in the gravitational energy. Now here we have a drop in gravitational energy. It is actually getting more and more negative. It actually has to change as it moves from point A to point B. So it's not constant. It doesn't increase, which is what B is suggesting. It actually decreases, and certainly D is not correct. So C becomes the correct answer. Question number 10. A strong magnet is moved past a copper block at constant speed shown. And what is the direction of the force acting on the copper block? Now, it's important to read the question. It's acting on the copper block? Well, as this magnet moves towards this here, what you're ending over here is you're going to get an eddy current that is occurring in front, and also an eddy current at the back due to Lenz's law. And as a result of a calculation, we can work out that the direction of the current will be in that direction. Because of Lenz's law, we want a north pole, and therefore this section here repels the north over here. Therefore, the north pole will apply a force onto the block to push it. Which way? To push it in that direction as well, because of the repulsion over here, but also the attraction on this side. And so therefore the force acting on the block will be to the right. The next question deals with Wien's law, which is in module 8. It says, what is the peak wavelength of the electromagnetic radiation emitted by a person with a body temperature of 37 degrees Celsius, which is 310 Kelvin. Well, this relates to Wien's law, which basically says the wavelength is equal to Wien's constant divided by the temperature. All you really need to do is add the values in. So you've got 2.898 by 10 to the power of -3, that is the constant on the formula sheet. Divide that by the temperature, which must be in Kelvin, which is 310. And when you get the answer, you're going to get 9.3 by 10 to the power of -6 meters. So therefore, A is our answer. Question number 12. Which graph shows the magnitude of the back EMF induced in a DC motor rotating continuously, but then at different angular velocity? So in other words, we're trying to work out the relationship between the angular velocity and also the EMF. Let's remind ourselves what EMF is. EMF is equal to negative delta phi over delta t. That is the rate of change of flux. Now I'm going to concentrate in this case on the t, the rate of change of time. Now what is omega? Omega is the rate of change of the angle with respect to time in radians. So therefore the time ends up being theta divided by omega. If we substitute that into our EMF, then what we get here is, and I'm just going to drop off the delta for the moment, we have negative phi omega over theta. Now what does this mean? Well, you can see now that we have a linear relationship between EMF and omega. Phi and theta are constant. Now I know it says a negative symbol there, but we're interested in the magnitude of the back EMF, so just the size. So being a linear relationship, therefore the answer is going to be D. Question number 13. The diagram shows an electron transitions in a Bohr model of a hydrogen atom. Which transition would produce the shortest wavelength of light? Well, the reminder here is that this dropping here is connected to Rydberg's formula. That is 1 over the wavelength is equal to R n f squared minus 1 ni squared. It basically means you get the shortest wavelength for the largest difference, and that makes sense. The shortest wavelength also means equal to basically HC over lambda. The shortest wavelength will result in the highest frequency. In the highest frequency, the greatest amount of energy for the greatest amount of drop. So therefore, the greatest energy drop, the shortest wavelength, will be the largest jump that we have. In this case, that's going from 5 to 1, and so therefore the answer becomes X. Question number 14. Which of the following statements correctly describes the gravitational interaction between the Earth and the Moon? Well, as you know, the Moon and the Earth are mutually attracted towards each other, and that is due to Newton's third law. That also means that they're experiencing a force. That means they're both accelerating. Now, the reality, of course, is we have the Earth relatively stationary and the Moon rotating around it, and so that force not only is a gravitational force, it is a centripetal force, but by its very nature, it is accelerating. The point here, however, is that we have A is accelerating, and it's correct. Let's have a look at the other answers. The net force acting on the Earth is 0. Well, I just established that's not true. There is a force acting on the Earth, and in fact, the Earth itself is rotating around a particular point, but it's actually really small, and so in essence the Moon causes the Earth to wobble ever so slightly. C, the Moon and the Earth experience equal and opposite accelerations. No, the Moon and Earth experience equal and opposite forces. That's Newton's third law, but it's not the same acceleration because their masses are different. So both B and C are incorrect. D, the force acting on the moon is smaller than the force acting on the Earth. Well, that is again against Newton's third law, so D is not correct. 15. Unpolarized light is incident upon two consecutive polarizers as shown. The second polarizer has a fixed transmission axis which cannot be rotated. I1 is the intensity of light after the first polarizer, and I2 is the intensity of light after the second polarizer. So how would I1 and I2 be affected if the transmission axis of the first polarizer was rotated? Well, in other words, this is our, let's say, our first position over here, and our second position, well, let's say, make it at some sort of angle like so. If this one is rotated here, then the intensity of one, which will be half of the original intensity, is going to stay the same. So in other words, rotating the first polarizer will not affect I1. However, the angle between the first polarizer and the second polarizer will change. And so therefore, the amount that will go through to I2, determined by Malice's law, will change. And so A is incorrect because I've said I1 doesn't change. Only I1 will change. Well, that's not correct. Neither will change. Well, D will, of course, not be correct because one of them will change, and therefore only I2 will change. Question 16. The sun has an energy output of 3.85 by 10 to the power of 28 watts. By how much does the sun's mass decrease each minute? Well, 3.85 by 10 to the 28 watts is basically saying 3.85 by 10 to the power of 28 joules every second. So we've got that amount of energy being emitted, but we want a drop in mass. So what we do is invoke E equals mc squared, and of course that is equal to E equals mc squared, and that means our mass is simply our energy divided by the speed of light squared. You can then calculate that value out, and you're going to get 4.3 by 10 to the power of 11 joules per second. But now, of course, we will need to multiply that by 60. Why? Because we're interested in minutes. So if we multiply that by 60, we're going to get 2.57 by 10 to the power of 13, and therefore B is our answer. Question 17. Now, look at question number 17. Two long parallel conductors X and Y are connected to a light bulb and an AC power supply. The conductors are suspended horizontally from fixed points using sensitive spring balances, and X is positioned below Y. Which statement is correct about the spring balances? Now, in essence, this is AC. So in other words, at any point in time, their currents are going to be going in opposite directions. So obviously for a momentary time, that current obviously stops, and so therefore what we have is no force due to the motor effect. The fact is that both are experiencing forces as they are in each other's magnetic fields, but for all intents and purposes, the majority of the time, the currents are in opposite directions. So with that in mind, and I'm using a green pen, they will always experience a force that is in the opposite direction, and that force, just due to the magnetic field, will be a value that will fluctuate but will always be equal. However, there is also the force due to gravitation, and so this will fluctuate backwards and forwards but be of the same size, but the force due to the gravitation will be in a downward direction for both, like so. So now you can see that automatically there is the possibility that the two forces acting on Y would go smaller, whereas at the same time the two forces on X will actually increase. So the two values on the spring balances will not be the same. That in fact X will be larger than Y. So therefore A is incorrect. The force measured on Y will be greater. We've just said that's not possible. The force measured on X will be greater. That is true. And then there is this continued reversal of which measured force is greater. This is always going to be true. If there's momentarily no force acting, then what's going to happen is you're going to have them equal, but Y will never be greater than X. So D is incorrect. Question number 18. An evaluated vacuum chamber contains a pair of parallel plates connected to a power supply, and a switch is initially closed. A positively charged mass falls within the chamber under the influence of gravity from the position shown. When the mass has fallen half the height of the chamber, the switch is opened. Which of the following correctly shows the trajectory of the mass? I've deliberately hidden or made small the possible answers because I want us to analyze this more closely. When the switch is open, what we end up having a field across like so. Now that field will cause these charged particles to experience a force in the horizontal direction. In other words, it will accelerate in that direction. But it is also falling at an acceleration in the downward direction due to gravity. Therefore, you have acceleration in both axes. The end result is that because it's a constant acceleration, you're going to get a straight line path. Now, what happens when the field is removed by the opening of the switch here? Well, it already has some horizontal velocity, but that will now be constant in the horizontal direction. Then, of course, it will still accelerate due to the gravitational field. So at this point, it will undergo projectile motion, with this being relatively straight like so. So if I now have a look at our possible answers, you'll see that when we look at our answers, the only possible answer is A. Question number 19. RH106 is a metallic beta-emitting radioisotope with a half-life of 30 seconds. A sample of this and an electrode are placed inside an evacuated chamber. They are connected by a galvanometer and a variable DC supply. A student measures the current when the power supply is set to 0. They then stop measuring the stopping voltage, and the stopping voltage is a minimum voltage needed to prevent the current flowing. A few minutes later, the measurements are repeated. How do these two sets of measurements compare? Now, this in essence is combining two modules. You have module 7 where we look at the photoelectric effect, and we have module 8 where we look at radioactivity. So in essence, this is a setup like the photoelectric effect, but instead of photons of light causing the emission of our particles, in this case beta particles, which are in essence electrons, then what we have is a radioactive source. So we have a rate of flow of electrons over here, and those can be measured by their current, which is what the galvanometer does, and also their energy can be determined by their stopping voltage. Now, what happens though over time? The fact is that there is a half-life, so the rate of electrons going across is going to decrease. Why? Because of the radioactive decay. That means the number of beta particles moving across will decrease. So as a result, the electrons will decrease, and so therefore the current is going to decrease over time. But what about the stopping voltage? Well, the stopping voltage tells us the speed at which they are moving across, or specifically their energy that they're moving across. That's not going to change. Although the rate of decay decreases, the actual value of their energy is not going to change. So when you look at the two sets of measurements, what's going to change? The current, but not the voltage. And so therefore, A is our only possible answer. Question number 20, a final question in the multiple choice section. We have a metal cylinder that is located in a uniform magnetic field, and the work function of the metal is phi. Photons have an energy of 2 phi striking the side of the cylinder, liberating the photoelectrons, which travel perpendicular to the magnetic field in a circular path, and the maximum radius of the path is r. And we have to work out, if the photon energy is doubled, what will the maximum radius of the path become? Now this again is tying to important concepts. First is the whole idea of the photoelectric effect, which is in module 7. And the second is the idea of charges and fields, which is in module 6. So to start off, we need to look at our kinetic energy in the before and the afterwards. So the kinetic energy initially is equal to the energy that they receive, which we're told is in the beginning 2 phi. But of course, they lose some of that energy due to the work function, which is phi. So our result of our initial kinetic energy is equal to phi. Our final kinetic energy is going to be, well, we're told it is, in this case, doubled. So now we have 4 phi. Of course, the work function is still phi, so the new kinetic energy is equal to 3 phi. So our kinetic energy increases by a factor of 3. Now, when we're looking this at in terms of a charge in a field, we know that there are a number of variables we need to take into consideration. Let's quickly review that. We know that they're going in a circle, so we have mv squared over r. We know also that is due to a magnetic field, the fact that that has a velocity, and we have a charge, so we have qvb. Now, if we then clean this up, you can see that one of the v's cancel out, and so what we get is mv over r is equal to qb. So there's our velocity, but let's think about the kinetic energy. If the kinetic energy increases by a factor of 3, due to the kinetic energy is equal to a half mv squared, that means our velocity therefore increases not by a factor of 3, but only by a factor of root 3. Now, looking at our situation here, we're interested in the radius, so I'm going to rearrange this. So what we get is r is equal to mv over qb. That means if my velocity is increasing by a factor of root 3, my radius increases by a factor of root 3. So the answer is D. So that ends our multiple choice section of the HSC Physics paper for 2021. I hope that has been helpful for you. Please like, share and subscribe, and consider buying me a coffee if this is useful to you. My name is Paul from Physics High. Take care and bye for now.